we've talked a lot about voltaic cells, and what we've seen is that voltaic cells have positive cell potentials, which makes them drive or occur as spontaneous reactions. This is electrolysis, and the electrolysis is the process of using an electric current to bring about chemical change, in practice using a power source to make a non-spontaneous reaction occur. And our analogy is going to be, so let's take remember our picture of a voltaic cell. And for a voltaic cell, remember we had an electron up here, and now we'll make this electron man. And we said that, so as the electron jumped off from, say, zinc and copper being the reactants, and they jumped all the way down here to zinc ions plus copper solid, that the difference here was what's called the cell potential. And we use that under standard conditions. And we realized that this, as a voltaic cell, was a spontaneous reaction. Okay. Now, what we're going to do is we're going to take an electrolytic cell is going to be the electron, and we'll still call him electron man, is at the bottom, and it wants to get up to the top. But this process of going up is a negative cell potential, so non-spontaneous reaction. And so the cell potential is negative, less than 0 volts. And so what we're going to do is, in order to make the non-spontaneous reaction occur, is we're going to pair it with, it's possible to do it with another reaction, but typically we do it with a power source. And the power source will take electrons at a higher potential, and this one we'll call electron woman. And if you apply enough power, you can drive a non-spontaneous reaction to occur. And again, you're coupling it with a power source that moves some reactions, or moves some electrons, and allows the other electron to occur. So in order for this to happen, the cell potential of our power source has to be greater and more positive. Let's take out that. It has to be more positive than the electrolytic cell is negative, so that E power source, E sub PS, plus E electrolytic is overall greater than 0. So we really are coupling things to occur, and we're coupling a power source to drive a reaction to occur that is otherwise non-spontaneous. That's what electrolysis is. Now let's talk about the construction of an electrolytic cell. And because it's non-spontaneous, everything can occur in one beaker. Our generic setup will be something like this. You'll have an electrolyte, And let's say that our electrolyte is sodium chloride. And you'll have two, and I'll draw them nice and big here, electrodes, and up here you'll have a power supply. And I will typically draw the power supply like in the shape of a car battery, and then I will connect it to the two leads on the car battery. This is a generic cell, well, generic in that it has an electrolyte. I've personalized it already by making the electrolyte sodium chloride, and in fact I'm going to make this sodium chloride liquid, and that's going to simplify some things for us. Things that it will do is, first off, this electrolytic cell for sodium chloride liquid has to have a temperature above 801 degrees Celsius, so we are at non-standard conditions. However, we will use standard cell potentials. E0 cell. Even though we're not under standard conditions, so this is an approximation, but it turns out to be a good one. Let's see what else. So under these conditions, there's no water. And there's only two half reactions that occur. One of those half reactions is for our reduction. Sodium, which will be liquid, plus 1 electron, goes to sodium, which turns out to be liquid as well, instead of solid. And this occurs at a reduction potential of minus 2.71 volts. Very negative, very non-spontaneous. Then we'll look at our oxidation half reaction. And the only thing that's around is chlorine. And chlorine will actually need, or chloride, 2 liquid chloride ions goes to Cl2 gas plus 2 electrons. This is an oxidation. And this one should be on our list, even though the sodium is not. I may have to add it for your exam. Chlorine. So this one is minus 1.36 volts. So they're both negative, and they're both very negative, in fact. But we can add it up. We can get our, well, let's do our overall reaction here. We have to take and multiply this top reaction times 2 while not multiplying our potential still. We have 2 Na plus liquid, cancel out our electrons, plus 2 Cl minus liquid. Those are the only things we have in here. Goes to sodium liquid, and this is one of the approaches that has been used to make sodium and to make chlorine gas. Our cell potential, or what we might call electrolytic cell, 2.71 minus 1.36 minus 4.07 volts. Wow, that's negative. But when constructing electrolytic cell, because it's negative, you can put everything in the same beaker. There's only one beaker here. And when we do this, let's say I typically draw my oxidation on the left. That is, oxidation is the anode, although I'm not too worried about that. My oxidation is going to take 2 chlorides in the liquid phase. They're going to come up here. They're going to give up 2 electrons and make Cl2 gas. And I'm going to draw bubbles here to complete the picture of that half reaction. Then on my other side, while my electrons are going through my wire, my cell potential has to be or my power source has to be greater than 4.08 volts, so that the overall 4.08 minus 4.07 is positive. And typically, of course, it will be much more than that, but it has to be at least that. And my electrons come over here where I do my reduction. That takes sodium and two of them. Did I balance that out? Oh, I forgot my two down there. Takes two sodiums in the liquid phase. They team up with two electrons and become two sodium liquids. And if you want to, you can draw a liquid coming down here to the bottom. So that's, I don't know what that is, but it's supposed to be a liquid. And it's going to drip all the way down here to the bottom and start collecting in a little pool, like so. So that's complete construction of an electrolytic cell. And be careful, because we've been very careful to do this with no water. Water complicates things. And I think what we've done is we've gone ahead and done everything we need on this page, on the previous page. Let me check here. Yep. So on previous page, now let's talk about a more complicated case of electrolysis. This example says, what reaction will occur when a power supply is attached to a solution of 1.00 molar sodium chloride? And let's see how many pages I got for this one. I do have 2 pages, so I'll try and figure out what's going on, and then I'll draw a picture of it on the next page. So we now need to decide which reactions are possible. So 1, decide which reactions are possible. And looking at our list of reactions that are possible, we have the reactions that we had on the previous pages. Those are going to be sodium aqueous this time and chloride aqueous. So I'll do my possible reductions here and my possible oxidations on the right. My possible reduction will be sodium, this time aqueous, plus 1 electron goes to sodium, which will now be solid. We're at T equals 298 Kelvin, which is 25 degrees Celsius, and sodium will be a solid. This is still minus 2.71 volts. Ooh, just got it in. And my oxidation from my previous page, 2 chlorides goes to chlorine gas plus 2 electrons. Only this time it's aqueous. And it's still minus 1.36 volts, like so. But now we have to consider the water reactions. And the water reactions are going to be reduction of water, and I know those are on our page. Reduction of water, which is here, oh sorry, here. This is going to be reduction of water. Come on, camera, catch up. There we go. And that's going to be minus 0.83 volts. And I'll write that down. So that's going to be 2 H2O liquid plus 2 electrons goes to H2 gas plus 2 hydroxides. And its cell potential will be minus 0.83 volts for reduction. Now the other reaction, let's see if we can keep up here, camera, is going to be this one up here where we have water as a product. If we move it over a tiny bit, we will see, I apologize for this. Let me just write it down. So 2H2O liquid goes to O2 gas plus 4 hydrogen ions plus 4 electrons at a cell potential or an oxidation potential of minus 1.23 volts. Remember, it's written as a reduction here, but when we flipped it, we have to take the sign. The other hint is that since we're talking about electrolysis, typically, although not always, but typically everything will be negative, and certainly the overall potential will be negative. Now, these are which reactions are possible. And what we've done is we know we have sodium ions, aqueous, chloride ions, aqueous, and we have water because it's the aqueous phase. Now, other examples you would take could be 1.00 molar, let's say, cesium iodide. And you would still take your water reactions, and you would also take your cesium and your iodide reaction. And then you do the thing that we're supposed to do next, which is find the oxidation and reduction that are closest to positive. And here we have this one is closer to positive than the chlorine. And here we have the water again is closer to positive than the sodium. And so it turns out that as soon as you try and do this reaction in the aqueous phase, you cannot produce sodium and you cannot produce chlorine. What you can produce is hydrogen and oxygen, and you're reducing and oxidizing water. So that's what we're doing. Let's write those out down here. I'll write out my oxidation. And I'll write out my reduction. Then I'll add them up. Noting the fact that, of course, I have different numbers of electrons in here, which I still have to cancel out. Add them all up. Let's see, I have 4 electrons here, so I'm going to multiply this reduction half reaction times 2. That gives me my electrons canceling. That gives me 4 hydroxides and 4 H pluses. So I'm going to talk about how we keep our acid for our H pluses and our hydroxides for our bases apart. So I'm actually not going to cancel them out. I end up with 2 times 2 waters plus 2 more. I get 6 H2Os. Goes to oxygen plus 4 hydrogens. Plus 2 hydrogens. for an electrolytic cell potential of minus 2.06 volts. And so when we construct this cell, we're going to do the same picture we already did before, the same idea. We're going to do the part that's in green here as an electrolytic cell. Our electrolyte this time will be 1 molar sodium chloride aqueous. One beaker, 1 power supply, 2 electrodes. Hook them up to the power supply. I'm doing whatever weird lines you want. I never told you what the electrodes were made out of. In electrolysis, it's almost always carbon solid or graphite. So that was one omission from my earlier one. My electrolyte is sodium chloride aqueous. It is 1 molar. And now I know my 2 half reactions. They're going to be take water on my oxidation side and turn it into oxygen and hydrogen ions. And, I mentioned the fact that I'm going to keep my 2 parts separate. So I'm going to put a sort of a divider down here. And if we were actually doing this in lab, this divider would typically be made out of cardboard. And cardboard's enough to basically allow ions to get wet and travel through it, so we don't have a buildup of positive or negative charge. And yet it does a decent job of keeping our acid and base separate. All right, a full drawing of an electrolytic cell has the oxidation and reduction half reactions drawn on it. So I'm going to take 2 H2Os. Those 2 H2Os are going to be giving up 4 electrons and producing O2 gas, bubble, 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 bubble. On the other side, I'm going to have 2 times 2, or 4 waters. Also doing 4 electrons and making hydrogen gas. Oh, sorry, I forgot to put my H pluses over here. Plus 4 H pluses. Over here, they're going to be making H2 gas plus 4 hydroxides. Bubble, 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 bubble. And in a lab, you can test to see that these are the reactions that are happening or not based on using a pH paper or a pH meter if you have enough room in your beaker. And finally, we have to put in that it has to be greater than 2.07 volts to drive this overall process to occur.